Yesterday we learnt about parallel prefix adder, right? So today we are going to learn about new concept called as add subtractor. Okay. So as you guys all learnt about adder, right? So subtractor will become easier. Okay. So if you learn subtractor means it will makes easy to study about ALUs multipliers. Okay. So after ALUs and multipliers, we are going to study about how RTL design workflow works and like how do we usually floor plan executes how we do floor planning and something related to VLSI chip designing. Okay, so yeah, before going to that, we need to complete this full subtractor, ALUs and multiplier. Okay, so today we are going to study an important topic that is called as subtractor. Okay, and it is a arithmetic circuit which helps you to like uh, just in how you in adder how you are adding an addition operation, right? Just like it was like working in some addition operation, right? Like that only, as the name suggests, like separator it's used to separate the your decimal bit operation. Okay, it's used to operates on your input bits. So before learning the full subtractor, remember that computers perform not only addition but also subtraction, right? So whenever a processor compares two numbers or calculate addresses or perform arithmetic operations or execute instruction, subtractor is required. Why? Because every time you're not going to add input bits, right? Sometimes you want you are getting some desired somewhat input, and you need only just some part of that input, right, to operate on that operate some task, right? So that's why subtractor is very much required in that type of situations. So a full subtractor is a combination logic circuit that can subtract three binary inputs. Okay, so what are the three binary inputs? They are A, B, and B in. Okay, A is nothing but minuend, B is subtrahend, and B in is borrow in. Okay, so just remember these three terminologies. Okay, like in full subtractor is a combination circuit that can subtract three binary inputs. What are the three binary inputs? A, B, and B in. Okay, A means minuend, B means subtrahend, B in means borrow in. Okay, so and you are going to produce two outputs. What are there? Difference and borrow out. Okay, so this topic is extremely important because it forms the foundation of arithmetical circuits, ALUs, processor, and VLSI design part, data part design. Okay, so by the end of this session, you will understand why full subtractor is used, needed, how it works, truth table derivation, Boolean expression, and K-map simplification, logic unit implementation, Verilog coding, and some real world applications. Okay, so where you are going to use this subtractor. So yeah, so before learning a full subtractor, let us quickly revise a binary subtraction. Okay, so in decimal subtraction, think you're doing a normal subtraction. What are you going to do for this operation, like line minus 3? What are you going to do? The output of 9 minus 3 is 6, right? So like in normal subtraction, a 5 minus 8, you can write here as minus 3, right? So you can write minus 3. What happens is 23 minus 17? 6, right? Now just think, okay? Here you have 5 minus 8, right? So this kind of subtraction happens in normal subtraction, okay? So what happens if you have another bit, okay? Another bit of input. So from that bit input, you can carry one borrow required means you like your answer in negative, right? So if a computer can't read this kind of negative, right, it can only understand 1 0, right? So that time there is a concept called as borrow, right? So you need to borrow from other bits so you can correctly evaluate that operation, right? So that's why we need like some this kind of operation, okay? So you will get why we have propagate borrow, right? So just see here 23 minus 17. How you are going to minus subtraction using this like normal method. How a first standard, second standard like students do subtraction, right? Like we write 23, 17. Then first we minus like 3, 7 by 3, right? So it doesn't happen. So you will carry 1 from 2 and it will becomes 13. 13 minus 7 will becomes 6, right? So after that 1 and 1 will become 0. So at this time we have borrowed something from the other, right? Next element. So that's why we need to propagate that borrow, okay? So if you are buying something from other bit, so you need to propagate during that time, okay? So that's why we have something called as propagate borrow. So same thing happens inside a decimal binary subtraction also. How? Just think you have a operation like yeah. What will happen for 0 and 0? It will become 0, right? Borrow also 0, difference also 0 because there is nothing difference. What happens if you subtract 1 uh, 1 minus 0? What happens for this condition? You will get answer is 1, right? And you don't borrow anything because your subtrahend is smaller, right? So this is subtrahend, okay? And this is minuend, okay? Sorry. This is minuend and this is subtrahend, okay? So when your minuend is smaller than subtrahend, okay? Then you are going to borrow. But here your minuend is 1 and subtrahend is 0, right? So you don't need to borrow in this kind of situation. And for 1 minus 1, you will get 0, right? So if you are easily achieving this subtraction, then there is no need of borrowing, right? So just look at the last case, okay? Here your minuend is 0 and subtrahend is 1, right? So you can't minus 1 from 0, right? How can like you have nothing? How can you minus nothing from minus 1? It not going to happen, right? So in that kind of situation, when your minuend is less than subtrahend, then you are going to borrow 10 from next column. What is meant by 10? In binary equation, 10 is nothing but, see here, this is a binary substitution, right? So what happens if you borrow 1 from the next column? What happens now? Your minuend is 0. So if you borrow 1 from the next column, then it will become something like 10, right? So what is the 10 in decimal form? 10 is nothing but if you convert this 10 binary form 10 into decimal form means it's nothing but 2. Then your a becomes 2 and 1 becomes and if you minus 2 minus 1 you will get the answer as 1, right? So that's how you are going to get 1 year. Okay. So and your borrow will become 1. Why? Because you borrowed something from the next column, right? So that's why you are getting difference as 1 and borrow as 1. Okay. Just I said, when a bit A is less than bit B, borrow 1 from the next higher bit. Borrowed bit counts as a 2 in the current position. Okay. 2 is nothing but 10 in binary equation. Okay. So subtractor are why subtractors are needed? Okay. So you can often ask like, why do we need subtractor, right? Why do we need to study this subtractor? Because it's a easy concept that we can handle easily, right? So if you ask this type of question, means the answer is very simple. Why? Because every digital system performs subtraction, right? How? Because there will be a time something like, just think you are editing a video. Okay. So if you are editing a video, you need to trim some part of your data, right? Why? Because to clean the data, right? If you are a good video editor, then what have you, like everything you have captured, do you post that into your some social media accounts like YouTube, Instagram, Facebook, like that? Not, right? So if you are a good video editor, means you are going to trim or edit some part of videos, and you apply like something designs, graphics for that. So it should look good, right? So like that only, there will be some situations where your input is like somewhat as data errors in it. Okay. So in that kind of situation, these subtractors will come into a picture. Okay. So it's like trimming the data and to clean the particular data like this. All you are going to get, why you need for this, why you are, this why your subtractor is used. Okay. So just think like that. So for example, like CPUs, whenever a processor executes A minus B, the ALU performs subtraction. Okay. So like your processor will say, I need to, like I am getting input like this, I need to do subtraction. So if your processor send this message to, then where this message will go, this message will go to this ALU. ALU is nothing but arithmetic logic units. Okay. So you will get better understand of this arithmetic logic units in next class. Okay. And for in ALU to perform the ALU to perform subtraction, it as comparator. You in previous class, like I also explained the comparator. Like what is the use of comparators? To compare the values, right? Like A less than A greater than B, A less than B, A equals to B, right? So it asks, like ALU asks comparator to like check whether what's the case we are getting here, because processor has told me to do do this step. So I need, it will ask, ALU will ask comparator to like give me the design, like what is the step or case I need to match right now. It will ask like that. Okay. So after that, your system is going to internally perform subtraction. Okay. So and it's also used in DSP systems. Why? So digital filters continuously calculate error values using subtraction. Okay. So if you are like a digital system processing, means you will get understanding like why we need subtraction here. Okay. So yeah, and these are the some other good examples for why and where you needed the subtractor. Okay. And like I said, in communication systems, like subtraction is used in error correction codes. Okay, like you are getting some kind of errors in the codes. So and in that type of situation, you use subtraction in CRC generators. Okay, so what does that do? It uses subtraction operations to correct that code. Okay, just remember the word CRC. Okay, so here you are going to use that subtraction operation, and also in VLSI data path design. Okay, so as I told, adder subtractor is also a fundamental building blocks in digital analytics. Why? Because if you are adding something, there should be a operation to negate that also, right? So that's why they both becomes crucial and fundamental building blocks. Okay, so before learning a full subtractor, we should at least undergo we should understand why we need all subtractor. Okay, so here, as you can see the in the block diagram, of subtractor has only two options, two inputs. Okay, so A and B, and two outputs D and B out. D is nothing but difference, B is nothing but borrow out. Okay, so and or borrow. So okay, from two table you will understand what are the procedures that's going inside that uh, uh, block diagram. Okay, so how we are going to perform a subtractor, for 0 0, if you are going to subtract 0 from 0, your output will be 0 and borrow will be 0. 0 minus 1, here you need to borrow 1, right? Why? Because you can't minus 1 from 0, right? So you will become 10. 10 is nothing but 2. Then your 2 minus 1 is 1, difference will be 1, and you borrow something, right? What is that borrow you borrowed? 1, right? So that's why you are getting 1 here, and this will be easy. There you have 1, and you are minusing 0 from that, so you will get difference as 1, and borrow as 0. For this you will get difference as 0. Why? Because your both the inputs are equal. So if you apply subtraction for that, so you're getting 0, and borrow is also 0, right? So you can easily derive truth table for this, and also easily write the boolean expression. Okay, so what will the boolean equation becomes, right? So it is what some look like XOR gate, right? So difference is somewhat looks like XOR gate output. So you are directly writing a XOR gate for that XOR gate equation for that difference. And for borrowed, just look here. What are you getting here? Okay, so A A hyphen B is nothing but you are doing something like AND gate. Before doing AND A and B, you are just making sure like that A is as a NOT gate. Okay, applying NOT gate to A. Why? Because just look here. When you are getting 1, okay, when you are getting borrow as 1, when you have condition like A is 0 and B is 1, right? So it somewhat looks like AND gate, right? So AND gate only activates when you have both as 1. Okay, but here you have 0, right? So just look into carefully into your truth table. If you have 1, A is 1, then you are getting output as 0 0 0, right? 0 0. And in another case, if you have A0, along with that A0, B is 1, right? So that time you are getting A as 1. Means if you apply A naught, what happens if you apply A naught here? A0 will become 1, right? So when both the inputs become 1, AND gate says that I am going to represent date as 1, right? So you have 1 year. So if for a year, both the inputs have 1, but you are applying not get to A, then it will become 0. 0, 1, answer is 0. Why? Because AND gate is going to activate your output only at when both the inputs are 1, right? So that's how you are going to uh, write your Boolean expression, okay? So there is also a limitations in subtractor, okay? And what are they? Like it can only add two single bits. Like what happens if you are getting a borrow in from another subtractor, okay? Like I think your subtractor is connected with each other. So what like in that time your borrow that is generated here, okay? This borrow is generated here, it need to be transferred to other, right? So other subtractor, that time you can't achieve that, right? So it only handles two single bits, that are the limitation. And also for same, like if you don't can't handle the three bits means just like then it is also can't be used in real world applications, right? Like ALU implementation, it adds three bits like something like that. And also it cannot accept borrowing from previous stages, right? So that's why these are the some limitations of subtractor, and that's why you are going to implement full subtractor, okay? So before going this, just practice to write Verilog code for this R subtractor, okay? So why do we need full subtractor? Why? Why? Because full subtractor is nothing but it can operates on three bits. Oh, it can operates on bits like A and B, and it also can accept borrow in from other subtractor. Okay, like the limitation that were present inside the R subtractor was has been fulfilled by like this full subtractor. Okay, so I hope everyone will know how to achieve this, right? Like just like in adder, how we are going to like convert that 4-bit input into 1 bit stage, and for these bits we are going to apply one like at least one full subtractor, right? Full subtractor, just like how we used to do in a full adder. Like for 0-bit group, we are assigning one full adder, this for one full adder and this one full adder, and for this bit 3 also one full adder. Like that only we are going to assign bit subtractor, okay? So what is a full subtractor? Okay, full subtractor is a combination circuit that subtracts three single bit binary numbers. Like what are they? A minuend, B subtrahend, and B in. B in is borrow in and from previous stages, and produces two outputs. What are the two outputs? Difference D and borrow out B out. Okay, so this is what the like textbook definitions looks like. Okay, and also I've explained here like what are the inputs and outputs. Okay, so how we are going to write a Boolean equation for outputs? We will get one idea once we are able to understand the truth table. Okay, so if you see the truth table, you will understand how to write this Boolean equation. Okay, so this is what the block diagram of our full subtractor looks like. Three inputs, two outputs, and you are going to give these three inputs like borrow in for the first stage, and this borrow out from the previous stage will be added to the next assigned to the next full subtractor. Like this, the process will continue in the inside the full subtractor for that particular number of bits. Okay, if you have 4 bits, then you should have four full subtractor, right? Like that, or you are going to understand the concept. So okay, now coming to the truth table, is just like how we learned for all subtractor, right? Your three inputs are 0, so difference will be 0 and borrow out will be 0. Like operation is looks like this: minus 0 minus 0 minus 0, you're going to get 0. Whereas Now we have something like this, right? 0 1 0. So what are the things you are going to do? Like operation looks like 0 minus 1 minus 0. What will you get inside this? Obviously you are going to get like, what is 0 minus 1? Minus 1, right? And minus 1 minus 0, again it will become minus 1. Okay, so that's why in that condition you need borrow, right? So that's why it's showing b out, means it requires like borrow. So, and if you are going to produce a borrow, means it's showing that, yeah, I am receiving borrow, so I need to borrow out. Okay, so why you need to do a borrowed? To send to the another full subtractor. Okay, so that's why it's thinking, when you are going to produce your borrowed, when you are using borrow in, then you are going to have borrow out, right? So that's how it's going to looks like. Okay, so next, same for this condition also, your difference become 1 and you're going to do borrow. Okay, so here you are going to get answer as minus 2. Okay, so if you are going to make minus 2 means, what is the difference you are going to get? Difference is 0. Why? Because look here, what is the output you have got here? Minus 2, right? So as I said, look here, I gave you 3 examples, right? 23 minus 27. Okay, so what you have got here? 6, right? So just like this, if you have, if you got answer, your borrow out. Okay, so you got your difference as greater than minus 2, minus 1. Okay, so that time you are going to get what is like, just think what your 2 answer will looks like in decimal. 10, right? You are going to 2 as 10, right? So if you do like, if you align this 0 minus 1 vertically. Okay, 0 minus 1 minus 1, you are going to write something like minus 2, right? So if you expand this minus 2 in the decimal form, means you are going to write as minus 10, right? So what did you get difference here under that particular line? 0. And where your 1 stands at to the next, right? So that's why you have here 0 as difference and 1 as borrowed. Okay, so like that only for other 4 inputs also works. Okay, so this is was the only case it's going to like confuse you guys, like how I got difference 0 here and how I got borrow out here. Okay, so I hope everyone is clear with this point. So based on that, you are going to based on this truth table, you are going to write some boolean expression, right? So just try to derive boolean equations by your self only, guys. Okay, why? Because if you practice it only in early stages, so then you can easily implement inside your design data path. Okay, so we have come to a concept called as derivation of difference equation using k map. Why you need to derive this difference equation? Okay, why? Because this is a concept that most of you guys easily confuses. Okay, so yeah, wait 1 minute. Okay, just for 1 minute. Yeah, okay. So why we need to like you can easily write Boolean equation, right? So why we need this difference equation for K map, right? Like using K map, right? Why we need this? Because if you are using this K map to derive a difference equation for a subtractor, means it's mainly used to make or to create a simplest and the most cost effective uh, circuit. Okay, so this K map is used to like minimize the hardware costs. Okay, so how it's going to minimize? Just see, like in previous class we learned something about Boolean equation, right? There it was not affecting. Why? Because uh, that time like it's very everything was simple, right? So we can usually implement it with like one XOR gate or a one AND gate or gate like that. We are used to write that difference equation. But here, look here, we are going to use just that's why I said to calculate Boolean equation. Okay, like I said, right? Boolean to draw a Boolean equation for the two equations using truth table, right? So just try. Okay, if you are able to succeed that Boolean equation for that equation, just count the number of gates you are going to get in that particular equation. Okay, so after getting that like number of gates you are in that particular equation, try to match it with this difference equation. Okay, like using K-map you are going to create a difference equation, right? Nothing but Boolean equation for that particular difference column. Okay, difference output, you are going to find a difference output using this K-map. Okay, so just try to evaluate, like keep it side by side and just count the number of gates you are going to use inside that equation that you have found out using Boolean equation for that using truth table, and this K-map Boolean sorry difference equation. Okay, so then you will know to understand why we have used here K-map only for this particular subtraction. Why we have used? Because it's used to reduce the number of gates. Okay, like if you usually write uh, Boolean equation using the old methodology, then for adders, other things it will succeed. Why? Because there are like a two table will be very simple. But for subtraction, when it comes to subtraction, if you write a Boolean expression, you can write Boolean expression, but they need to use too much number of gates. Okay, so that's why I'm telling you guys to write a Boolean equation using truth table. So after, if you understand yeah, I'm writing Boolean equation, so you will get to know why we are using K-map here. Okay, so if you count that number of gates inside the Boolean equation, then it will be too much. So then you will think like, yeah, I am using too much of gates inside this particular Boolean equation. So to keep it short and to make my hardware design like low cost efficient, like that, you will think like that. And yeah, and you will see, yeah, if I use this K map, means I can keep my hardware cost as less, like that you are going to think. And you will think that, yeah, I can proceed with this K map for finding Boolean equation or difference equation. If you think like that, yeah, you are in a correct way. Okay, so these are the difference we got, right? So just look here, your AB is 0 0 and B in is 0. Now you got B out as 0, right? Wait. Yeah, okay. See, look here. We were talking about this K map, right? So what is the meaning of this K word? And K means nothing but Karnag, okay? Karunag map, okay? Like you see here, KRNUAG, Karunag map. So this is nothing but this is a checkerboard, okay? So you always calculate this only. Like if you need to write a checkerboard like this, and you need to calculate the step, okay? So just like your inputs like 0 0 0 1 1 1 0, you need to like this, you need to follow the same pattern only, and afterwards first time like b in 0, and for that b in 1, like vice versa you need to change the values like this only. We need to follow this checkerboard pattern, okay? So why? Because this is the pattern your Karunaka map uses to derive the difference equation, okay? Just observe the pattern, okay? So if you observe this came up pattern, you will notice some things, right? What is the thing you are noticing? That your one appears alternatively, right? So it's a like it's a form of checkerboard pattern, okay? You're getting like 1 0 0 1 0 1 1 0 like that. Your one is changing alternatively. So using this checkerboard, can you make a group of two? Can you make a group of two? No, right? Can you make a group of four? No, right? Can we make a group of eight here? No, right? So why? Because you are getting your ones as alternatively, right? So you can't group them, right? So that's why we can't group them, right? So the important concept that you need to understand is that normally in K map we simplify expression by grouping adjacent ones, right? So but here no adjacent cell exists, right? Every one is isolated, right? Like here one is at one end and here one is at the one, right? It looks like this only, right? So you can't group them. So therefore no simplification is possible. So this type of things are called as irreducible function, okay? So just keep the terminology in your mind, irreducible function, okay? So after that, if you are know how to write a checkerboard, then write a canonical SOP, okay? Since you are now your grouping is impossible. Why? Because you don't have any adjacent ones. So write all mini terms, okay? What are the mini terms? Look here. What is your first input looks like? 0 0 1, right? Sorry. Look here. 0 0, like you are these are the things you have achieved, right? So when your difference is getting here, here only, right? So when are the borrow out you are getting, there are four cases, right? These are the four cases, like these three and this one are the four cases you are getting borrow out, and these two, this one, and this seven. At the seventh case, you are going to get a difference as one, right? So, oh, sorry. So we need to like how to derive this equation after when you don't know how to group the adjacent cell, right? So if you do like if you don't have option like how to group them adjacent cell, you have something like I said mentioned in reducible function, right? So when you have the this type of reducible function, then you want to write a canon of canonical SOP, sorry, canonical SOP. Okay. So for the canonical SOP, there will be three steps. Okay, like we need to list many terms where D is one. Okay, so difference is one. What are the where is our difference is one? The second, right? When A is zero, B is one, and B is zero, and 0 0 1 for this, and 1 0 0 and 1 1 1. You need to take these many terms. Okay, like m1 m2 m4 and m7, you are going to write like this. Okay, like three inputs a b and b in, 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 like this you are going to group. And if you like summation, like if you put over summation on that particular terms, you can write in the form of like this, right? Like a b b in means this is nothing but a and get b and get b in. Okay, why you are writing this? Just look here. What is your answer? What is the answer you got here? For the first equation, 0 0 1, right? So what is the place? You only have one B in, right? So if you have one for that particular input, leaving that input, you need to write other two input as like a not get. Okay. So you need to keep everything like every input as in one state. Okay. So if you try to keep like that, then you will get something called as XOR pattern. Okay, so you will get to recognize that XOR pattern. So you will get equation like this. Okay, if you list many terms of that particular, like I said for D, when D is 1, if you break that many terms from that particular table, and if you try to write a equation, and it's something like looks like this. Okay, you are going to like apply OR gate when your input as 1, and this is something looks like XOR gate, right? So you are going to easily achieve, right, XOR pattern. Okay, so you need to identify like what pattern it looks like. Okay, before like solving this subtraction, you need to understand the every gate logic patterns, right? How to write that logic patterns, you need to understand that, and you will get something what like this. Okay, so this is somewhat looks like two XOR gates cascaded with three inputs, right? Like first you are going to achieve A XOR B, and after that input is achieved with uh, this output of A XOR B will be cascaded with B in, right? It's going to apply XOR operation with that output. Like this, you are of using K map. Okay, why using K map? Because if you apply K map means, just look here. Why we are using K map? Okay, even though if you don't apply K map means, you will get the final equation like this only. Why? Because I thought you K map means like you need to get interested on this kind of situations. Okay, if you are getting a boolean equations where that handles like too much of gates, then you apply K-map means just try to learn what is K-map and how it operates. Okay, so if you're going to apply like Karanaga map, then it will search for what inside the K-map, what it search for. It will search for like adjacent ones. Okay, if you don't have any adjacent ones, you can't group them. Okay, so then if you can't group them inside the K-map, then there will be no simplification. Okay, so K-map is a like it's a procedure to test whether you can reduce your Boolean equation or not. Okay. So just before, like I told something like you need to find a Boolean equation using the simple method, and you need to try like evaluate your difference equation with the Boolean equation you got using simple method, right? Just I said to that line to get you interest on these topics. Okay. So what is K-map? K-map is nothing but it is a process of reducing your logical gates inside a Boolean equation. Okay. So how it's going to reduce? It's going to group your adjacent ones. Okay. Yeah, using like in checkerboard, based on the checkerboard that you have created, it will like group a number of adjacent ones, and it will give you a simpler explanation. Okay. So like that, sorry, it will give you expression, simplest expression on that grouping. Then you will able to get that particular equation, and you are going to reduce the number of gates used in that equation. Okay. So that's why you are going to use K-map. I hope everyone got why we are using K-map. Okay. Look here. We are also tried to derive Borrow equation using K-map. Okay. But here we got a situation like we are getting some adjacent ones, right? So what are the things you are going to do if you are getting a adjusting like adjacent ones? Okay. Now if you got adjacent ones means first you need to break down from truth table. We need to break down what are the steps we need to follow. First you need to follow the steps like where you are getting that a B out one, right? If you are getting a B out one, we need to break down that from get that mini terms from the truth table. Like I am getting at M1, M2, M3, and M7. These are the steps I am getting B out as one, right? From the truth table. So after that, you need to group, okay? When you are going to group, where you have adjacent ones here, right? This is the step you have adjacent ones. So okay, if you have here as adjacent one, okay, you're going to look here. You are just have three groups here, right? Why? Because you have group 0, 0 and 0, 1, right? And 0, 1 with 1, 1. Why? Because this look here. Here you have adjacent ones. Here also one. Here also one. And for this AB11 and AB01, there is also adjacent group, right? So that's why you have group into three groups. Okay. Okay. I hope everyone got how to pair. Okay. Just look here. This is your group one, where your AB is 0, 1 and B in is 0, 1, right? 0 and 1. We have been for that. You are going to write a pair like that. Okay. Like A, what is your A value is 0, right? For 0, you are going to get a mini term as A not great. For like I said, you need to keep your every bit in 1, right? So for that, to follow that procedure, you written your A not, and dot means and you get B. Okay, you got your first pair. Okay, now you are going to group. Okay, why? Because you are adjacent. How you are going to group? Using adjacent place you are going to group. What are the adjacent place you have? AB00, AB01. This is my first adjacent. Okay, this is my first adjacent value. So I'm going to keep my adjacent values there. Yeah, what are the adjacent values I have? AB00 and AB01. Okay, these are my adjacent place. And where is my, you are getting the value like adjacent value when you have b in 1, right? When you have b in 1, that is the time you are getting adjacent ones. So that's why you're showing b in. Now I'm going to group based on adjacent values. So I have adjacent ones when I have b in as 1. Okay, so that's why you're grouping that values. So how to write this equation? Why you are writing this equation? Why? Because what you have here, ab as 0 0 0 comma 1, right? So for this kind of situation, just look what is your values not changing here. What is the value not changing here? Like here, so look here, you can see this group, right? A B 0 0 0 comma 1. What is the value not changing here? A value, right? So you need to keep that value. Okay, the not changing value need to keep, should be kept. Okay, so you are going to keep A. So A is value is 0, so you're going to write A naught. Why? Because you need to keep it as 1. Okay, and after you need to keep B in. Why? Because that is the basis of group you have made. Okay, that's how you are going to pair. That's how, this is the condition for the pairing. Okay, and also check group 3. Now you have AB 0 1, AB 1 1. Okay, so when is you are getting adjacent ones? When you have B in as 1, right? So when you have B is 1 and this value. Now look, what is the value that is not changing here? When you have b is 1, right? So that's why you're keeping b. Okay, why you have written only b here? Why you have written only b here? Because your b is 1, right? That is not changing, so you kept b as 1. And also the pair, like the place where you have as one adjacent one, you have kept that. Okay, so this is how you are going to pair. After pairing, you can easily write the equation. Okay, so why I left this condition? Why? Because here either we are not getting, like b in as 0 and b out as 1. Okay, so you're not getting anything, any values. Okay, this is how you're going to simplify your using k-map. Okay, so like I said, right, for difference equation I used k-map, right? But I didn't get any simplified answer. Why? Because I didn't have any adjacencies. Okay, so but here I got adjacent ones, so I can, like, I had an option to simplify, right? Just compare this value. Here I have, look at this D, look at this D, right? So here I have something, three inputs, right? So just compare this. What we have, two inputs, right? Equation with the two inputs, OR gate, AND gate, right? So this is how you're going to simplify. Okay. So just don't use this. Okay. If you are writing a Verilog code, just try to write your own Boolean equation. Okay. And just count that number of gates in that, and also number of gates here. Okay. So this will make this, some difference. Okay. This will get some difference. Yeah. And we got our difference and borrow out from K-map. And after that, you need to write like this and everything. Like you can do like using different uh, equation. You can like using that how many gates they have. Like that, you can draw a logic gate implementation. For borrow path also you can do like that. So after that, just try to practice like how to get a full subtractor using two alpha half subtractor. Okay, plus OR gate. Like I have said, this will be the task for today. Like try to solve this full subtractor using two half subtractor plus OR gate. This will be the, like, just if you want like how we are going to solve it, just take a screenshot and try to solve it on your own. Okay, so this is the task for this. Like you need to send this by within Monday. Okay, just try to solve this task and send within Monday. And after that, you need to create your Verilog code and just try to implement this. Okay, so that's it for this class. Okay, guys.